Mathematical induction presents two kinds of difficulties. One is in understanding the structure of the claim that you're making, and the other is often involved in the algebra that one has to do to prove one or both of the claims that you're making is correct. And so let's do an example of a very, very important relationship, maybe one of the most important relationships of all of mathematics, that really requires mathematical induction to be done correctly. And so we're going to work on that. First, let's review what the conditions are that you have to prove are correct in order to use mathematical induction. So you're trying to prove, never, ever, ever start to prove anything without writing down what it is that you're trying to prove. So you're trying to prove this. I'm going to use quantifiers and the like. Is that you've got some proposition. I'm going to call it, oh, call me crazy. I'm going to call it P for proposition. And you're trying to prove that P is true for every natural number. So there's the quantifier for every little n in the natural numbers P of n. And that's a Boolean. So you don't have to say P of n is true. P of n is a Boolean. It's either true or false. It's a statement. And so there's what it means. And that involves two separate proofs in order to establish that this is the case. This is the principle of mathematical induction. One of the things that you need to do is prove P of 1, or the base case. That's usually, but not always, the easiest. The other thing that you have to prove is an implication. Now, this is reasoning implication, not truth table implication. Truth table implication includes the case you've got P, let's not use P, you've got Q implies R, and truth table implication deals with the Q is not true case, but when you're reasoning, you know Q is true. So there are two different kinds of implication. This is not a commonly made or emphasized difference, and so let's emphasize it. There's truth table implication, and there's real people doing real reasoning implication, and we're doing the latter. Okay, so the situation that we have here is, back to mathematical induction, is we need to prove that P of n implies P of n plus 1, and again, that would be for every n. So there are the two things you have to prove. P of 1, remember, that's a statement, so that's true or false. Or you need to show that it's true. And then for every n, P of n implies P of n plus 1. And some people would skip the for every here because it's implicit anytime you have implication that it's every time this happens. But it's much more clear to you and to people who are reading your work if you include this quantifier for every n. So let's make sure that we do it. Okay. So now this is kind of useless unless you have an actual proposition in mind that you would like to prove is true, and it's even better if that proposition is useful. And so let us talk about one of the most useful propositions in all of mathematics, and this is called the geometric series. And we've studied sigma notation, so I'm going to write it that way first because it's a little bit easier. It takes less ink. And then let me write out a few terms, because whenever you have sigma, it's always good to write out a few terms. So let me just check something here. Perfect. Okay, so the geometric series says the sum I equals 0 to n. That's going to be the parameter, the proposition that we're proving involves n. And what we have is r to the n. So let me just make a note here that r is a constant. And I've made a typo, so let me fix it. It's r to the I. It's not r to the same power. It's r to the 0, r to the 1, r to the 2, so forth and so on. So my apologies for that. And so here's a big long sum. When n is 2, you get r to the 0 plus r to the 1 plus r to the 2, big woo, it's got 3 terms. But when n is 10,000, now we're getting somewhere. And that's one of the advantages of having mathematical induction, is that you don't have any doubt that what you did that worked when n was 2 also works when n is 10,000. Okay, so there is a closed form formula for this sum. So the sum is not considered closed form because it has so many terms, but the formula that I'm about to write down is actually factored and something that you can do with very, very few operations. So this is a very, very useful shortcut, and it's a fraction, and the bottom is 1 minus r. Now that ought to get you scared, because that's how I got this scar in 8th grade. That was when in a situation where the bottom of a fraction was 0. Bad idea. So we know now that r cannot be equal to 1. Okay. The top is 1 minus r to a power, and the power is n plus 1. So this is the geometric series formula, and I can't say this too much. This is one of the most useful formulas in all of mathematics, and so there's the situation. Now that's a formula. A formula is implicitly a proposition. The proposition is that it's true for all possible inputs into the formula. In this case, we really only have one input, that's n, and so we're asking whether this formula is true for all n. So to turn this from a formula into a proposition, I just need to kind of tweak it a little bit, and I'll do that this way. So instead of just having the formula, I'm going to say for every n, this formula holds. Now we have a proposition. So that is P sub n. P sub n is the proposition that those two things are equal. It's not one side of the formula. It's not the other side of the formula. It's not the equation that's involved in the formula. It's the assertion that the formula works. It's the assertion that the formula works. This is a logical statement, not an arithmetic statement. And so it's something to keep in mind that we work with a proposition or a statement when we are doing mathematical induction, and in other kinds of proofs as well. Okay, so I also promised that I was going to write out the summation notation. So here, to save space and ink, I have used summation notation, and let me now write out what the sum is. And I'm being very, very careful about how I say this. I'm sorry, I'm writing very, very carefully. I'm writing so carefully. And in fact, I'm going to write so carefully twice. So now I have not written out the induction step. I have not done any proposition. I have now just written out an equality of two expressions. This is just arithmetic here. And so here is the summation as given above, and I've written it two ways. One is as 1 plus r squared. The dot dot dot, we used to say that meant you continue in the same pattern, but you know what it means now? That means, uh-oh, I'm going to have to use mathematical induction. There is no such thing as dot dot dot. When we're introducing people to this, we kind of use that as a simplification, but there is no such thing. The only way to work with something like this is to use mathematical induction, and you have to turn it into a statement first, and there's that. I've also written out some of the justification for doing that. As an algebra reminder, r to the 0 is 1, r to the 1 is r. A lot of people leave those out, but then you break the pattern. The pattern should be r with an exponent, and if you have a couple of terms that are not written that way, now the pattern is much less clear, and you'd be much better off if you, in fact, did not skip this step. So don't skip this step. Okay, so that's the sum that's on the left. And now we want to go into the mathematical induction part and prove that that formula is correct for every natural number. And so So here's what we've got to do. We've got to do the base case, and then we have to do the induction step. I forgot to mention that part. So, so there is the base case and the induction step. Okay, so let's jump in and start proving stuff. Now it sounds scary to say we're going to start proving stuff. We're just going to do some calculations, and the way we're proving stuff is saying, oh yeah, these calculations came out the way we said they were going to. That's a way to prove things, is to do a calculation and see, oh yeah, it came out right. So that's what's going to happen here. Okay, so P of 1 is the proposition that the sum I equals 0 to 1. The general case is I equals 0 to n, but this is P of 1, so it's I equals 0 to 1 of r to the I, and this is supposed to equal a fraction. The bottom is 1 minus r, and the top is 1 minus r squared. So this is a mathematical formula that's either true or false, and it's actually it's got some complications, but let's see what's going on here. I'm going to work on the right side separately. Remember that 1 minus r squared factors as 1 minus r times 1 plus r. And so I'm going to kind of combine some steps here. The top is rewritten this way, and now we have a 1 minus r on top and a 1 minus r on the bottom. And so those are going to cancel. Remember, r can't be 1. And so, so what we're left with is 1 plus r. So this fraction is actually just equal to 1 plus r. So that's good. So now let's write out the terms of the summation. And the terms of the summation are r to the 0 plus r to the 1. That's the sigma notation version. And it's like, oh no, they're not the same. Never mind, let's go home. No, they are the same, because r to the 0 is 1. It doesn't matter what r is. And r to the 1 is r. And in fact, you can't write this down, but as far as for making a diagram, you can draw an arrow from one to the other and say, yay, they're equal. Aha, the world is saved. We got the same thing. So that's a proof. We calculated it one way, and we calculated it another way, and we got the same thing. That proves that they're equal. Okay. The next part's a little bit trickier, and so that was the base case. So let's look at the induction step. And in the induction step, we're going to have to do some honest algebra. Not like there's such a thing as dishonest algebra. And so let's just kind of jump right into it. In the base case, we are given that P of n is true. So I'm going to write that down, and I'm going to use the word given. If you just write it down, it's just throwing darts at a mathematical dartboard, and it doesn't mean anything. You have to describe what it is that you're doing when you're working on convincing someone that something is true. And so I'm going to write that we are given that the sum I equals 0 to n r to the I is equal to the fraction with 1 minus r on the bottom and the top being 1 minus r to a power, and that power is n plus 1. That's given. We are assuming that this is true. That's what the induction step says. It says assume the formula is correct for n, and now we're going to have to establish that it's correct for n plus 1. Okay, well, so what we're going to do is, this is where you get to be a little bit more creative with the algebra, but here's the deal. We're not interested in what we just wrote down. We're interested in the sum I equals 0 to n plus 1 of r to the I. That's one side of the formula when I is n plus 1, and we're trying to prove P of n plus 1. So that's one side of it, and this is supposed to be equal to a fraction with 1 minus r on the bottom and 1 minus r to a power on top. And it's going to look kind of like nitpicking, But in fact, this is the right way to do this. If you skip this step, you're more likely to get things wrong. The power that we get here is one more than the top index of the sum. And so I am going to write it that way. It is one more than the top index of the sum. Some people say this is doing an extra step, and I say if you don't do this, you're skipping steps, and skipping steps is bad math. So, and bad logic and bad computing. So skipping steps is bad, unless you're playing hopscotch or something. Anyway, so this is the left side, and here on the other side is, that's p of n plus 1. And so we have written that down, and so that is what we try to prove. Hey, you know what? We ought to say that's what we're trying to prove. So I'm going to amend this a little bit and say that's what I want. Now, the reasoning that I'm going through is much more clear with these two little words. I'm given something, and I want something else. And so if I just write down the two formulas, that's just writing down two formulas. That's just throwing darts. And so, or throwing dice with formulas on them. Doesn't mean anything. You have to connect them with something that describes the steps of your reasoning. Okay. So here's what I'm going to do. I'm just going to do a little bit of algebra, and that will establish that the induction step is true. So we'll start with the sum I equals 0 to n plus 1 of r to the I. And because we know summation notation, I can make the following step. And this is exactly the kind of thing you're looking for. I'm going to highlight this after I'm done writing it. So this is the sum I equals 0 to n of r to the I plus r to the n plus 1. So what I've done here, first I'll let you look at it. So that's what we're interested in calculating. So we're going to start calculating it. And there are an infinite, not an infinite, but there sure are a huge number of ways to split this thing up. And I have chosen the way that includes one of the expressions from the given step. We're given some facts about this sum when it goes up to n, and now I've got the sum when it goes up to n. So now I have something that I can do. I can substitute for this term right here and see what happens. So let me just kind of, that's kind of the creative part, is that you are looking in doing the algebra for any of these induction steps to find something that from what you're given, and then you can substitute and then do the algebra. So I've circled those in red. Okay, now, so I'm going to use what I was given. So what I have here is the following. This is equal to, it's a fraction now, 1 minus r on the bottom, and 1 minus r to a power on top, and this time the power is just n plus 1. So what I've done right here, this is the fact that is given to me as part of mathematical induction. This fact is given. If you have something that's given and you don't use it, your proof's probably not valid. So let me just make a note here that this was given. Oh, and I didn't finish the expression. So we still have to add on r to the n plus 1. And now we're going to do a little algebra. And so what we're going to have here, I'm just putting these over a common denominator, so you can study this in more detail from the scan. And now if I look at the top of that fraction, there is some cancellation, and so the cancellation is there's a minus r to the n plus 1, and now from putting it into the lowest common denominator, making it to do the actual addition of the fractions, there's a plus r to the n plus 1. So those cancel, and this now neatened up a little bit is equal to a fraction still, 1 minus r on the bottom, and the top now has 1 minus r times r to the n plus 1. That's what we're looking for. That's it. We've done it. So the thing that we're looking for I'm going to kind of highlight this in green, is the fraction 1 minus r on the bottom. Everything has 1 minus r on the bottom in this whole thing. And on top we have 1 minus r to the power, 1 more than n plus 1. And what we have done is establish that the sum is equal to a fraction. Sorry, I shouldn't talk and write at the same time. It's equal to a fraction, and that fraction has 1 minus r on the bottom, and the top has 1 minus r, well, to the power is 1 more than n plus 1. And that's algebraically equivalent. I'm trying to get this to where it shows up as to what you have here, what you want. So the geometric series formula that takes that long sum and changes it into just a little teeny fraction is correct, and we have proven it by mathematical induction, and now you can use it for any value of n. And you will. Many times in the course of your career, you will use this, and so it's a useful thing, so you should enjoy it.